Alright, this is Chapter 4, Section 3. So we're looking at binomial distributions. So there are other types of distributions. There's geometric, negative geometric, multimodal, stuff like that. We're only going to be covering binomial in this section. So the key being bi is in 2. Okay, so it's a probability distribution that's specifically binomial, essentially, which means you fit into 2 categories. Those 2 categories could be a mixture of things. And specifically for binomial, you must have these particular properties, which is a fixed number of trials. There are other types of distributions where you could have more unknown number of trials. They must be independent, meaning one trial cannot affect another trial probability-wise, right? You must be 2 categories, hence the bi, right? One of 2 things. And the probability must be the same at all times, so it can't keep changing after each one, right? Which does play into the independence, but it can also change. So keep in mind if you're doing a population, the 5% rule. So you don't have to worry about replacement at that point once it becomes a population. Okay, so let's look at the following scenarios and let's decide if they're binomial or not. Okay, well, let's say I'm selecting 20 university students and looking at their class rank. Well, that's a problem. That's not 2 things. That's like a lot of things, isn't it? Because class rank could be anything. It could be any number in there of many people, correct? That's failing rule 3. So if I draw 5 cards from a deck without replacement, record whether they're red or black. Well, that's 2 things, red or black. That's good. That's what binomial is. But there's a slight problem without replacement. So as a result, the one draw is dependent on the previous draw, isn't it? So doesn't that fail rule 2, that they're not independent, right? Because the second one is dependent on the first one as far as that. All right, let's say that the college student is selecting. You want to find 5 kids on the dean's list, right? So you go and ask them, are you on the dean's list? Yes or no? Go to the next one. Are you in the dean's list? Yes or no? You keep doing that until you find 5. Well, that's a problem because that is not a fixed number of trials. That's fails number 1. So how long is that going to take you? We don't know. Let's say you select a door out of 3 and you either win a prize or you lose a prize, right? 2 categories, win or lose, right? If either has a prize behind it or not, you are given the choice to take the door or swap to the other one being shown that you did not choose. Okay? Well, the problem is that changes the probability because they took away a door, right? That changes the probability. Okay? So originally you were picking out of 3 doors, now you're only picking out of 2 doors. That changes the probability, right? That's the Monty Hall problem. You can look that one up. There's some nice videos on that, but that doesn't work, right? So yes, 2 categories, win or lose, but the probability changes. It's not the same each time, so that's a problem. Okay, so the binomial formula and many of the other probability distribution formulas are very similar, right? There's basically 3 components. There's the success and failure, so the P and the Q is the success and failure part, and this is the count, the number of ways it could happen, right? So these are common notations that are used in calculators to represent combinations, right? This is the manual way of calculating combinations, where n is the number of trials and x is the number of successes. So for example, if you're doing the coin scenario where you're flipping a coin 3 times, right? You could get a head, correct? 1 heads and 2 tails. Was that heads first? Is that heads second? Or is that heads thirds, right? So you can get tails, heads, tails, correct? Or you can get heads, tails, tails. Or you can get tails, tails, heads, correct? So those are just different combinations of, or permutations, sorry, of, or different orders of getting basically heads, first, second, or last. So, and you have to think about, where and how many you get. You get 1 heads or 2 or 3, and move it around essentially. Okay. So let's do an example here. So let's say we have 60% of the population believe in life on other planets, so the fun people, right? And you select 10 people from the U.S. population. So you're selecting 10 people. What's the probability? Exactly 7 of them believe in aliens, so 7 fun people. So that means you have 60% success, right, which is believing in aliens, and 40% are failures. Correct? Okay. So that's our numbers to go with. That's the basis for our formula, right? All right, so let's look at now the probability of 7, which is what we want. Probability of 7. So we have 10 factorial over 7 factorial, 10 minus 7 factorial, times 60% to the 7 times 40% to the 10 minus 7. Okay? So you notice when you simplify this down, this is the probability of 7. It's 10 factorial. This is 7 factorial times 3 factorial, right? And this is 60% to the 7 and 40% to the 3. Notice 7 plus 3 gives me 10, 7 plus 3 gives me 10. So it should always add up essentially. And one thing I want you to notice is here when I put the x, then n minus x, here is n minus x and x. So depending on which book you pick up, it's going to be one way or the other. I prefer this way where I put the number I'm shooting for in the front so I can just remember, you know what I'm saying? But either way is fine. Okay, so my recommendation is don't put this all in the calculator in one step. You will get it wrong because you need a series of parentheses. You get one parenthesis wrong, you will get it wrong. Do it in the spreadsheet, right? So there's 3 parts. There's the count, there's success, there's failure. Multiply them together, get your answer essentially, right? So let's do a spreadsheet. Right, so we have count, success, failure, right? Answer. That's what we want. Okay, so I'm going to do that, do that, do that. Okay, we'll make this a bit bigger so we can see it. So my count is the factorial of 10, right? So that's the way you do the 10 exclamation mark in a spreadsheet because they use word commands in spreadsheets, divided by parentheses factorial 7 times factorial 3. So the most common mistake students make is they forget the second set of parentheses because you need to divide by the entire denominator. Right, I'm sorry, the entire denominator needs to go under the 10. If you don't put those second set of parentheses, it only divides by the 7 and multiplies. Okay, so there's 120 ways, right, of doing it if you rearrange them essentially. Okay, let's see. So the success rate is 60% to the 7, right? And this one is 40% to the 3rd. Okay, so failure percentage, success, and the number of ways it could happen, right? So click times click times click. I get about 21% essentially is what my answer should be, right? Okay, so if I look at my notes, probability of 7 is about 21% chance if I'm going to find 7 people, right? Could I have more or less? Yes. So other times I'm going to find, more than 7 or less than 7 people that believe in aliens essentially. Okay, let's try one more here. Let's try a fractional scenario. So let's say that we have 1 out of 5 people have visited the doctor in the last month, right? That's what we're going to do here. Okay, you select 10 people at random. Okay, determine the probability exactly 3 of them then visit the doctor in the last month. Okay. So we want the probability, come on pen, all right, the probability of 3 people went to the doctor, right? So out of 10, so 10 factorial, right? So 3, and then 10 minus 3 factorial, and this will be 1/5 this time to the 3rd, and this will be 4/5, right? Because 1/5 success, 4/5 failure. 10 minus 3. Okay, so remember, these must add up to 1, right? It did last time, it was 60%, 40%. And then this should be 10 factorial, and this should be 3 factorial, 7 factorial, right? These add up to 10, and then 1/5 to the 3rd, and then 4/5 to the 7th, right? And then 7 plus 3 is 10, right? So the question is, what is this probability? Okay, let's try it and compare to last time. Alright, so if I do this, I get a factorial of 10 divided by, oops, a parentheses factorial of 3 times a factorial of 7, close paren. So last time we had 7 and 3, this time we have 3 and 7. Is that going to make a difference? It's really not, because you're just multiplying two things together. They're the same, essentially. So I'm still going to get 120. The success rate is not going to be the same, right? So this one is 1/5. Make sure you put the 1/5 in parentheses. Again, the most common mistake is parentheses in this chapter, because it's the whole 1/5 to the third, right? And this one here is 4/5, right? And that one's to the 7th. Okay, so success, failure, and the number of possible ways it could happen. So click times click times click. So about 20% essentially is what this one is, right? So we go back to our notes. It's about a 20% chance of getting 3 people that went to the doctor if you ask them, essentially. Okay, let's look at some scenarios. So these are all singleton scenarios. Let's look at some multiple scenarios now. So let's say 80% of the population knows how many trillions of dollars the U.S. is in debt. If you randomly select 5 people in the U.S. population, what's the probability at least 3 of them know the debt in trillion? Again, we're still calculating manually in Excel. Okay, so that is not a single probability. That's asking at least 3, so that's 3, 4, or 5, isn't it? Okay, so we have 3, 4, or 5. We want to do all 3 of those probabilities. So we can do this directly or indirectly, essentially, right? Okay, so let's go to our spreadsheet here and make another tab, right? And I'm going to copy these here. Okay. Paste this here, and we'll put number here, I guess, right? So 0, 1, 2, 3, 4, and 5 are the ones that are possible. Okay. Bold. Good enough. Okay. So we have 0 people, 1 people, 2, 3, 4, and 5 essentially is the possibilities that could happen, right? Okay, so the count, right? So either way, it's the factorial of 5, right? Because no matter what, we're asking 5 people, do they know what the debt is, right? Divided by, parentheses, the factorial of, this is 0 successes, and then factorial 5 minus 0 successes, correct? Because the number of successes is going to change from 0 to 5, correct? So if I drag this down, boom. Okay, so here, right, it's 3 successes, and 5 minus 3 would be 2, right? So 5 successes, 2 failures, correct? All right, so success chance here is 80%, so 80% to the power of 0, right? And we drag that down, right? And we get our successes and failures, right? 80% to the 3, okay? So failures is 20% to the power of parentheses 5 minus the number of successes, correct? We can actually, well, that's number of successes. So we can put number of successes, I guess. I don't know. Just put num, I guess. Okay, so we'll drag that down. Okay, so we're going to multiply this through. So click times click times click, and we get our answer, right? So the probability of 0 successes is this, probability of 1 success is this, 2 successes is this, 5 successes is this, right? So if we add them all up, we should get 100% if I did it correctly, which I did. All right, so we want the direct method, and we want the indirect method. Okay. So what is the question asking? Let's go back. The question is asking 3 or at least 3 of them know the debt. Okay, so if it's at least 3, that's the 3 plus the 4 plus the 5, correct? Indirectly, you would do it this way. 1 minus the bracket, I'm sorry, parentheses, 0 plus 1 plus 2, correct? And you get the same answer, correct? So just either those indirectly or those directly. So what did we do and why? So directly versus indirectly, right? You either do it directly or indirectly, correct? Either way, you get the same answer. depending on the scenario, one might be easier than the other, one might be impossible, so you might have to do one or the other. So you have to know how to do both, essentially. Okay, so I chose this example because it's symmetrical, so it doesn't actually make any difference. It's the same amount of work either way, because it's 50-50 essentially. Okay, let's try one more scenario where we do it direct and indirect, doing it manually. And this is going to come up in the next section also, or the next video, when we do the functions and the way they work in the spreadsheet. So let's say we do the aliens and other planet one again. So we want to know at least 5 of them believe in life on other planets, correct? That's what we want to know. And now we're again selecting 10 just like last time for the alien, correct? So we want to know 5 to 10 essentially. So that's a lot of different probabilities, isn't it? Okay. And again, this is still the alien one, so it's 60-40. Okay, and we're selecting 10 people. Okay, so let's go to here. Let's copy this, and let's go to another tab and paste it. Okay, so now in the alien one, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? This is a lot more. So you can see how this gets pretty big quickly, so this is a better way of doing it, essentially. Okay, so the count here is 10, right? So there are 10 possibles we're picking from, divided by the factorial of this number of successes, times the factorial of 10 minus that right there, correct? Right? So overall, successes and failures must add up, correct? So you drag that down, fills them all in, correct? So if I do 6, I get 6 successes, and then 10 minus 6 is 4 failures, correct? If I do 7, right, it's 7 successes, and then 10 minus 7 is 3 failures. Okay, so the success percentage for the aliens is 80%, correct? Those are the fun people. Wait a minute. Wasn't it 60% for the it was 60% for the aliens. I was 80% for the last one, wasn't it? Yes. Okay, 60% believe in aliens. I'm sorry. So 60% to the power of the number of people. And we can drag that down, right? So 60% of the 5. Perfect. So failure is 40% of the unfun people who don't believe in aliens to the power of parentheses 10 minus the number of successes. Correct? Close that off. Drag it down. Right? So if I have 7 successes, that means 3 don't believe in aliens, essentially. All right, so my answers are count times success times failure, and then drag it down. Right? So if I add this up, it should come up to 1, right? Which means all the possibilities. It does. So we have direct and indirect methods of calculating this, essentially, right? All right, what does the question ask? The question asks at least 5, right? So that's 5 or more. So directly, that's 5 plus 6 plus 7 plus 8 plus 9 plus 10, correct? That's directly. So indirectly is 1 minus the other ones, which is 0 plus 1 plus 2 plus 3 plus 4, right? So either way, we're going to get about 83%, correct? Okay, so long story short, one way versus the other might be easier. One way might be impossible, depending on the question, because especially if it goes to infinity in some scenarios we're going to do in later chapters, you can't do the infinity ones, so you have to do the indirect method. Okay, this will help us in the next video too with the computer functions. Okay, so there's always that one problem, right? And this is the next one we're going to run into here, which is why I give this problem. Let's say we want to know the number of girls in birth, I guess, right? So you have 945 couples. So what's the probability I'm going to get 460 girls? Okay, so I want to know the probability of 460. Okay. All right, so it's 945 people giving birth, right? So 460 factorial, and then 945 minus 460 factorial, right? There's that. So we'll assume it's 50-50. It's not really 50-50. It's slightly more chance of a girl, you know. Just the way it is. Right. So 460 and then 50%, right, to the power of, didn't leave myself some room there, but that exponent should be 945 minus 460, correct? That should be the exponent. I didn't leave myself some enough room there. 945 minus 460. Okay. Let's do this in the spreadsheet, though. Okay, so I'm going to just go back to here, and I'm going to do the count, which is the factorial of 945 divided by, parentheses, the factorial of 460 times the factorial of 945 minus 460, close paren, close paren. Oh, that didn't seem to work. Well, maybe if I do the other ones there, right? So that's 50% to the 460, right? And then 50% to the parentheses 940 minus, 945 minus 460, correct? Okay, did I get the right numbers there? Yes, I did. All right, well, let's try to do the answer. So this times this times this doesn't seem to be working. Oh, man. So he said there was a problem, right? So we read this here. What does it say? So I get it. Can I get it to pop up? All right. Does it tell me the error? No. Okay, well, here's the general problem, right? What is 945 factorial? So 945 factorial is 945 times 944 times 943 times ... all the way to 3, 2, and 1, isn't it? That number is so large, right, you would never be able to quantify or even visualize how big that number is. It's bigger than any number this computer can handle, or any other computer, essentially. So there is a limiting factor around somewhere around 400 or something like that, where the computers can't handle it. It was so big. So you end up having to estimate with other methods, essentially. So, long story short, there is a limitation to this formula, and we'll get into other things like Poisson. So, yes, you can set it up. Right, I can give my values, I can set up the formula, but I'm not going to get an answer essentially because, right, 945 factorial is too large is essentially the problem. Okay, all right, that's the end of this section.